Okay, so welcome back, and this is the last in the videos looking at the carboxylic acid derivatives pack. In this section we're going to be looking at the reactions of the esters, and we're going to be looking at making polyesters. So you're going to need your notes, and we're on page 18. Okay, so this is hydrolysis reactions. Now you've come across these before when we were looking at the hydrolysis of a nitrile. So basically hydrolysis means breaking up but using water. Okay, so it's splitting a bond, that's the Lys part, but it's using water. Now quite often we will do this in acid or alkali conditions, as the reaction with just plain water is too slow. So you can think of hydrolysis as being the opposite of esterification. So if I take a carboxylic acid and an alcohol under acidic conditions, it will turn into water and an ester. Under the same acidic conditions, the ester and the water will break back up into the carboxylic acid and the alcohol, and that is called hydrolysis. So the acid in this case is acting as the catalyst in the reverse reaction. So here is my ester. And this is methyl, there's my methyl group, propanoate. So it's methyl propanoate. And we've got my water. And that's going to split the ester back up into the component carboxylic acid and alcohol parts. So I've made my propanoic acid, and I've made my methanol. Okay, so looking at that in terms of displayed formula, if we start with ethyl propanoate, so I've got 3 carbons of my propanoate, that's come from my carboxylic acid functional group, and then I've got the 2 carbons of the alcohol functional group. Now where it was joined together, if you like, this is the joining bond between the two groups, between the alcohol and the carboxylic acid. That's where I'm going to split it up again. Okay, so just moving that up a little bit so you can see it. And then we've got some water. And we're going to split those, and as I said, we're going to split across this bond here, because this is where we join them together. And we're going to get our carboxylic acid. In this case, this is propanoic acid. And this obviously is in the presence of a dilute acid, and we've also got our ethanol as our other product. Okay, now there's one last bit, and the eagle eyes of you will have spotted this. This reaction needs to be reversible, so it needs a reversible sign, and I'm going to put the acid on there. And that is one of the disadvantages of doing this. This reaction is reversible, and in fact when we study this later on, when we look at equilibria, you'll find you get quite a lot of ester, water, carboxylic acid and alcohol in your reaction mixture. So it's one of the few cases where the equilibrium is pretty much in the middle. So not only can we do hydrolysis reactions with acids, we can also do them under alkali conditions. Very similar reaction. Remember, this is hydrolysis, so it's the water that's breaking it up, and it's catalyzed by the hydroxide. Now because the hydroxide is there, instead of getting the free acid, you're going to get the salt. So again, if I start with my ester, this one is ethyl ethanoate, and I've obviously got my sodium hydroxide, and this makes sodium, it goes to sodium ethanoate and ethanoic acid. Notice it is not reversible. Okay, so this will give you a better yield, but it'll give you a yield of the salt and the alcohol. Then what you can do is cool this reaction mixture and add excess of a dilute strong acid like HCl, and that will basically what we call reprotonate, or add a proton onto this species, and that will give me my carboxylic acid. So there are advantages in the fact that it's a non-reversible reaction, so you get much higher yield of your salt, but then you do have to do a secondary step to actually get the acid. And if we look at the bottom of that page, you can see that we've got that displayed formula. So we're starting with propyl methanoate, so that's the methanoic acid, and we've got propan 1-ol there, so we've got methyl propanoate. We're making the salt of our carboxylic acid, so that's sodium methanoate, and we've got propan 1-ol as our alcohol. Okay, so we're on page 19 of your notes. Now, this was a very nice little experiment that we would usually do here, but it was an additional practical, so I'm not going to go over this in great detail. But basically, this is soap making. So what we're basically going to do is take our triglyceride, this is this molecule here. You can see it has this ester functional group in it. So this would be a triester, if you like. And what we can do with sodium hydroxide is we can do exactly the same experiment as before. We can hydrolyze it and break it across these bonds here. Okay, so you end up with this being my alcohol. This is my carboxylic acid. So we end up with glycerol, or as we would call it, propan 1,2,3 triol. Because I've got an OH group there, CH and OH group there, and a CH2 and an OH group there. So that's glycerol. Okay. But that's not what we're really interested in this case. In this case, we're interested in the soap, which is the sodium salt of these carboxylic acids. So you would end up with these three. So you'd end up with 3 lots of C17, so that's my large hydrophobic tail, joined to a hydrophilic sodium salt, and that's what makes the soap. So I'll have 3 of those, and that's my crude soap. Okay, so we're on the last section of the notes, and we're looking at polyesters. So polyesters, as their name suggests, are a type of polymer, but they're made rather than adding across a double bond, they're linked through an ester functional group. So to make them, we either need a diacyl chloride or a dioic acid and a diol. So here is my diol. This is my ethan 1,2-diol. So it's got 2 OH groups. And this is my dioic acid. So it's got 2 COOH groups on it. Now the reaction is going to be exactly the same as the one we've just been studying. We're going to lose the hydrogen from the alcohol, and we're going to lose the OH group from the carboxylic acid. And we're going to join those two together to make an ester linkage. But that is going to happen at both ends. And so we're going to link lots and lots of these in what we call an AB format. So we'll go AB, 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 and so on. Okay, so what we're going to get when we add these two together, and we're going to draw it as 2 repeating units of this polymer. So I'm going to start with my alcohol functional group. So I've got that linking oxygen and that linking outside of the box. And then I've got my 2 carbons to another oxygen at the other end. That is joined on to the carboxylic acid functional group, and then I've got these 1, 2, 3, 4 CH2 groups. So I've got CH2, and I've got those 4 times because there's 1, 2, 3, 4 of them. Then I've got another C double bond O, and that is joined on. Now that would be 1 repeat unit, because if I pick that up and put it there, it would then be repeated. Okay, so because I've been asked for 2 repeating units, I'm just going to draw the second unit in. Okay, so I've drawn in now my second repeating unit. So basically what I've done is I've picked up this bit of my molecule and I've moved it to there. What you have to be careful of is that these groups kind of follow on. So basically this C double bond O would join onto this O here. The classic mistake is to put these 2 oxygens at either end. Okay, and that wouldn't be right. You have to think about it in repeating units. So basically that is my 1 repeat unit. If I pick that up and put it there, it would be identical. Okay, so that's 2 repeating units of my polyester. Okay, so this next ester, polyester, we're going to have a look at. This time we've got our dicarboxylic acid. This is benzene 1,4-dicarboxylic acid. And we've got ethan 1,2-diol again. And again, you've got these repeating units. So here is my alcohol, then I've got my carboxylic acid, then I've got my alcohol, then I've got my carboxylic acid again, and then I've linked it through. Okay, so again, if we were to draw that, okay, and we would pick that up and put it there, we would see it would be repeated along the chain. Okay, so those were types of AB polymers because you had alternating carboxylic acid and alcohol groups joining together to make your ester functional group. In this case, with things like polylactic acid and 3-hydroxybutanoic acid, they have the alcohol and the carboxylic acid on the same molecule. So this can be made into a polyester using only one type of monomer. So here is my chemical I'm going to use. Again, I'm going to lose the hydrogen off of that, and I'm going to lose the OH group of the carboxylic acid. So I'm going to get my oxygen, which is bonded because I'm only doing a repeat unit for this. So I've got my C, my CH3, my H there, my C double bond O, and that is then linked through. And that will be one repeating unit. I take that up and I put it there and keep going down the line. Okay, again, another example here, 3-hydroxybutanoic acid. So again, I'm going to lose my hydrogen from my OH group, and I'm going to lose the whole of that OH group there. And then again, I'm going to write it out. So I've got my oxygen going outside of the box, showing that that chain is extending that way. I've got my C, my H, my CH3, and I'm moving along to a CH2 group, C double bond O, and then this line again is where it's repeating in that direction. Again, if I picked it up and put it there, you would see it is repeating down the chain. Okay, so that finishes the last section of the carboxylic acid and derivatives pack. I'd remind you that the questions, or at least question 1 and 2, need to be uploaded on Friday, and you should have done and self-marked question 3 by Wednesday. But that's all for now, so I'll speak to you soon. Take care, stay safe, bye-bye.